In this video, we'll talk about how we apply integration by parts to a definite integral. Okay, so first I want to make a note of what integration by parts looks like in general with a definite integral. So if I have an integral of the form u dv, so if we've already identified what to let u be and already identified what to let dv be, and it goes from a to b, when we do integration by parts, we'll get uv, but we'll have to plug in the b and the a into this and subtract, minus the integral from a to b of v du. So let's box this. So this is our key formula of integration by parts, but with a definite integral. Let's do an example. So let's suppose we want to evaluate this integral from 1 to 12 of ln of t over the 4th root of t dt. So I want to briefly talk about what would happen here if we had tried u sub. So with this example, u sub, if we were to try it, the most natural choice of what to let u be would be probably the ln of t. And u sub is not nice in this example, since let's just look at what happens if we were to try it. Since if u were equal to ln of t, then du would be equal to 1 over t dt. And if I look at my integral, I don't quite see 1 over t dt. This is not quite what we have. So not quite what we have. And sometimes when that happens, it would still be possible to convert our integral completely in terms of u if we were to use this u substitution again and isolate for the t so we could plug in. But if we were to do that here, it turns out it doesn't make the integral easier to do. If anything, it makes it harder. Okay, so that's one indicator that u sub is not going to be helpful in this problem. So let's try integration by parts. So let's try integration by parts. So I want you at this point to pause the video for about 1.5 minutes, 1.5 minutes, to try an integration by parts, just to the point where you get your new expression, your new integral, and see if you can determine, is that easier to do? 4, 3, 2, 1, pause the video. Pause it for 1.5 minutes just to try an integration by parts and see if it makes your integral easier. Alright, so hopefully you've done that. Hopefully you paused it for about 1.5 minutes to really try this. So we need to let u be something and dv be something. Okay, so I need to have u be something that I know how to take the antiderivative of, and something where its derivative is... Sorry, let me say that again. I need to pick u in such a way that I know its derivative, and hopefully that its derivative is easier than what it is. So I'm going to pick it. I'm going to let it be ln of t. If I put the ln of t over where the dv is, I don't know the antiderivative of ln. We talked about it in the last video, but that actually requires integration by parts to figure out antiderivative ln of t. So I'll let u be ln of t and dv be the other stuff. So 1 over 4th root of t dt. And then I got to figure out du, which would be 1 over t dt, and what v is. So to get v, it'll be helpful to rewrite this 1 over the 4th root as t to the negative 1/4. So if I rewrite it as a fractional power and then bring that t term to the top, that's where the negative exponent comes from. Because I know how to do the antiderivative now, this is just reverse power rule. So I add 1 to the power, that gives me t to the 3/4. And then I would divide by 3/4, which is the same thing as multiplying by the reciprocal, 4/3. Alright, so from there, we are ready to plug into integration by parts. And we'll get uv 4/3 t to the 3/4 ln of t minus the integral of v du. So that'll give us 4/3 t to the 3/4 times 1 over t dt. And then I got to include these limits. So I need a vertical line here and put 1 and 12. And on my integral, I need to put those limits of integration, 1 to 12. All right, so we can simplify this now a bit, because this 1 over t, I can think of it as t to the negative 1. And then if I have t to a power, like 3/4, times t to a power, like a negative 1, we add the powers. This would be t to the a plus b. So we can simplify this a bit. So that, simplifying it, we'll get 4/3 t to the 3/4 ln of t. Need to plug in 1 and 12 into it still. And then minus, I'll get the integral from 1 to 12. Let's pull the 4/3 to the front, because it's a constant. And then t to the 3/4 times t to the negative 1 is t to the negative 1/4 dt. Okay, so from there, that is now an easier integral to do. We end up getting 4/3 t to the 3/4 ln of t. Need to plug in the 1 and the 12. Minus 4/3. Now we're ready to do this antiderivative. But we've actually already did the antiderivative of t to the negative 1/4 over here. The antiderivative is 4/3 t to the 3/4, doing some reverse power rule. Okay, and then I need to plug in 1 and I need to plug in 12 into this. So one thing that can help the algebra here before I plug in is to notice that both of these terms have this t to the 3/4. So let's factor that out. So let's factor out t to the 3/4. It'll just make the algebra a little bit easier. So this is going to be equal to t to the 3/4. If I wanted to, I could also factor out the 4/3, because that is also common to both of them. But I'm just going to go ahead and factor out t to the 3/4. So when we factor that out from the first term, we will be left with 4/3 ln of t. And from the next term, we'll be left with minus 4/3 times 4/3, which is minus 16/9. And I need to now plug in the 1 and the 12 into this. So let's plug in 12 first, and we'll get 12 to the 3/4 times 4/3 ln of 12 minus 16/9. Okay, and then I got to subtract what I get when I plug in 1. So we'll get 1 to the 3/4 times 4/3 ln of 1 minus 16/9. And this could be simplified a bit, because ln of 1 is just 0. And 1 to any power, like 1 to the 3/4, that is just equal to 1. So what this gives me, after I do that simplification, is 12 to the 3/4 times 4/3 ln of 12 minus 16/9. And then after that, we have this minus 1 multiplying negative 16/9. So I'll get plus 16/9. So if I was asking you to work this out without a calculator, this is the point where it would be okay to stop. We have done our antiderivative, we have plugged in our numbers, and we have simplified it kind of as much as we can without a calculator. If we were to use a calculator and round this to about 3 decimal places, we end up getting, this is about 11.677. So just to recap with this example, the key ideas were, 1, if I have a definite integral and I need to do integration by parts, where those limits of integration come into play, so how we plug those numbers in. And the other big idea, I think the more important idea, was why did we do integration by parts? Why did it help us? Because typically on a quiz or on an exam, when I give you an integral problem, I'm not going to give you an integral problem and say, okay, do integration by parts, or okay, now do U sub. Ultimately, that's a skill that I want us to develop, and we're practicing that now in these lecture videos, figuring out what method is best to use. And sometimes, like we did here, we'll have to investigate one method first, like we did U sub, and it wasn't helpful, and we may have to try a different method. We'll get better at recognizing the best method with practice. So in terms of our goals for this section, we have finished our second goal, which is doing more examples. In the next video, we will up the difficulty a little bit and look at a more complicated example related to an application.